Okay, seems like the majority of people are here, so I might as well start. Anyway, welcome to the last tutorial of the term, and especially welcome to Bowen, who is probably his second tutorial or something like that. Welcome, welcome. Always glad to see new faces here. Okay, so for today, I did want to talk a little bit about contest free, but unfortunately, there's still actually someone who hasn't done it yet, which means that I'm not actually allowed to talk about it, which is a shame. So I guess we'll just have to move on to the actual topic of today, which is maths, otherwise known as number theory. So today we're going to be covering two questions. The first one is going to be based on prime factorization, and the second one is going to be based on game theory and probabilities. So one thing about number theory that you should probably know is that there are a lot of differing topics inside it, and all of them are sort of completely different. So, on top of the topics that we're covering today, there's going to be stuff in the lecture that I can't possibly cover all in the tutorials, like the greatest common divisor, lowest common multiple, Euclid's algorithm, modular arithmetic, combinatorics, and exponentiation, right? There's so many of these topics that they don't even all come up in the problem set. In the problem set, they don't cover GCD or LCM in them as well. So yeah, basically what I'm trying to say is that the scope of this tutorial is actually quite small compared to what you learn in the lectures. So make sure you do check out the lecture slides and the problem set when you're training for the final exam. Also, I do want to say that maths is one of my weaker topics compared to all the other topics in competitive programming. This just means that I might take a little bit longer to think about questions when they're asked. So all I ask is that you're a little bit more patient with me if that occurs. Finally, at the end of today's lesson, I'm going to share some advice about exam technique in preparation for your finals. All right. So I guess we'll get started with the first problem of the day. And this problem is called division. So by the way, I'd just like to check who has watched the lecture for this week. Again, totally fine if you haven't. I just like to know. Can I get some yes and no's or hand raises? Finished like 5 minutes ago. Nice. Very prepared. Just read the slides. And I assume everyone else has not. That's totally fair. Completely fine. And don't worry, you won't actually need the lectures. In my tutorials, I like to sort of just cover everything anyway, just to make sure, just sort of people who haven't quite watched the lectures yet, because I understand that it's a very short time between Monday and now. Anyway, let's actually look at this problem now. So again, this first problem is going to be about prime factorization. And typically, you're not going to need fast exponentiation for this problem, but I'm just going to throw it in anyway, just to sort of show you guys what it looks like. So, division. Oleg's favorite subjects are history and maths, and his favorite branch of mathematics is division. To improve his division skills, Oleg came up with t pairs of integers pi and qi, and for each pair decided to find the greatest integer xi such that pi is divisible by xi, but xi is not divisible by qi. Oleg is really good at division and managed to find all the answers quickly. How about you? So the input, you're going to get a single integer t, which is the number of pairs. Then you're going to get t lines containing two integers pi and qi. So notice that pi is going to be smaller than 10 to the 18, which means that you'll need long longs to store p, and qi is only going to be up to 10 to the 9. So these two bounds are actually very important, and we'll see why when we're analyzing the complexity. So pi and qi are the ith pair of integers. Output, we print t integers. The ith integer is the largest xi, such that pi is divisible by xi, but xi is not divisible by qi. One can show that there is always at least one value of xi satisfying the divisibility conditions for the given constraints. So you don't need to prove this. This is just given to you in the exercise. So here is our sample input here. We can see that we have 3 test cases, and then we have 3 pairs following that. So looking at the first pair here, looks like the answer is 10. So 10 is divisible by 10, but 10 is not divisible by 4, right? So that's why we've chosen x to be equal to 10. And this is going to be the largest x such that those conditions are met. For 12, we can see that 12 is divisible by 4, but 4 is not divisible by 6. And finally, 179. 179 is divisible by 179, but 179 is not divisible by 822, obviously because 822 is larger than 179. And in each of these cases, this number is going to be the largest number, such that these two conditions are met. Pi is divisible by x is not divisible by q. And so, of course, the question is to actually find the x for every single pair. Notice that even though they have this pi and qi, the pairs, obviously, between the pairs, they don't actually matter. So the answer to this one has no correlation to the answer to this one, and so on. Okay, so hopefully that makes sense. I'll give you 5 minutes of thinking time for this problem. And if you have any questions, you can ask me during this time as well. Okay, so hopefully that's enough time for you guys to think about it. Before we dive into it, did anyone have any observations they'd like to share? Give you a little bit of time to type. If not, then I guess I'll share one of my own. So I guess we can start with the following observation here. Let's say, to begin with, if P is not divisible by Q, what should we set X to? I'll repeat that again. If P is not divisible by Q, what should we set X to? Right, we should actually set X to P. Why is that? Well, okay, so firstly, we have to check that it meets the two conditions. So P is divisible by X. Well, P is divisible by P, right? So that's going to be true. P is not divisible by Q. Well, we've made this assumption here. So if we set X equal to P, then this condition will also be true as well. So both conditions will be met. Not only that, clearly since we're finding X that divides P, well then X is going to be smaller than or equal to P, right? So by choosing X equals P, this is going to be the maximum possible X for this result. So in other words, if P is not divisible by Q, then let X equals P. And that will be the maximum answer that we can get. Right? Hopefully that makes sense. So now all we need to do is consider the case where P is not divisible by Q. P is divisible by Q, my bad. P is divisible by Q. Okay. So I guess for this particular problem, when we see ideas of divisibility, one of the things that we could probably think about is prime factorization. So whenever a problem comes across with like terms such as like multiplication, division, divisibility, powers, and square roots, those sort of things are sometimes it is easier to deal with the numbers in this question if we prime factorize them first. So let's start by prime factorizing P here. So hopefully, as we all know, this is the fundamental theorem of arithmetic, that any positive integer, you can write them as a product of prime powers. So for example, let's write P can be written as the product of primes to some sort of power. So each of these P1 to Pk are going to be primes. And A1 is going to be some sort of power, right? For example, 21 equals 3 times 7, right? Very simple example here. And these powers are all 1. Okay. So we also know that P is divisible by Q. So would anyone like to suggest what this prime factorization of Q must look like then? More specifically, what should the prime factorization of Q look like in relation to the prime factorization of P that we have up here? Yeah, exactly right. It's going to be some subset of it. So another way of doing the subset, or another way of thinking about this, is we're actually going to just have the same primes, exactly the same primes, all to some sort of power. But the condition, of course, is that bi must be smaller than or equal to ai for all b and a, right? And so that's basically just the same thing as taking the subset. Make this smaller so it'll, oops, Make this a little smaller so it all fits on one screen. Okay. Yeah, so basically what we're doing is we're taking the same primes from the original P, and we're basically just going to lower their powers by some amount, right? Potentially, we could lower these powers down to 0, right? So Bi could actually be equal to 0, in which case that prime no longer exists. But we can always write Q in this sort of form here. The exact same primes with just lower powers. And similarly, when we're trying to find an x, since we're trying to find an x such that x divides p, we can do the same thing here. So we know that x will also be of the form something like this. Yep. So that's how we sort of look at divisibility in terms of prime factorization. Okay, so we've now worked out what divisibility looks like, but now we kind of have to look at what not divisible looks like. So what we want here is we want for x to not be divisible by q. We need to look. There's going to be sort of two ways that x might not be divisible by q. The first way is going to be q has a prime that x does not. If q has an extra prime, and the primes I'm talking about are these. If q has an extra prime that x does not, then clearly x is not divisible by q, right? That's the first way we could do it. And the second way we could make x not divisible by q is have a prime x that is less than the power of the same prime in q. Right, so for example, if maybe we'll look at some examples here. If x equals 2 squared times 3 and q equals 2 cubed times 3, well then clearly x cannot be divisible by 3, right? Because this power, the power of this prime is going to be larger than x. If all the primes are smaller than or equal to x, so for example, 2 is smaller than or equal to 2 and 1 is smaller than or equal to 2, then of course we have divisibility, which is what we touched on before. So these are the sort of two ways that we could possibly affect x so that x is not divisible by q. But hopefully we can see that number one, q has a prime that x does not. This is sort of out of the question because at the very beginning we've shown that p is divisible by q and p is divisible by x. So all the primes are going to be exactly the same. There's no way that q is going to have an extra prime that x does not. So we can kind of cross this one off our list. And so what we have left is just 2, right? Have a prime in x that is less than the power of the same prime in q. So in other words, we're going to have at least one of these ci. We're going to have at least one of these ci going to be smaller than a bi. So basically what we've ended up with is we need to choose an x that looks like this, which with the prime factors, the same prime factors as p. All the ci have to be smaller than or equal to ai, so you have to match this condition. And also for one of them, for at least one of them rather, ci is smaller than bi. So I guess the question now is, how do we actually choose the x so that this is maximized? Well, first thing we can sort of start off with is that you would only ever really want one of them to be less than bi, right? If one of them is less than bi, then x is not divisible by q. If two of them are less than or equal to bi, well, we can just make one of them not less than or equal to bi, right? We can increase the power of one of those, and then the condition is still met because one of the ci is smaller than bi, but we just get a larger x in return. So we can conclude that instead of at least one, we have exactly one. exactly one ci less than or equal to bi. And then what about the rest of them? Well, clearly we want the largest possible for the rest of the prime powers, and we have this condition that ci is less than or equal to ai. So we might as well just set ci to equal to ai for all of them. And that's exactly how we're going to pick our x. We're going to we're going to set all of these ci to equal to ai, right? The original powers in P. And all we're going to do for exactly one of them, we're going to choose one of them and we're going to set it equal to less than or equal to bi, less than bi. And so of course, if you want to set it less than bi, well, we don't want to make it too much smaller than bi, right? Because we're sacrificing the largeness of x. So we might as well just go the largest possible such that it's less than bi. In other words, we'll set it to bi minus 1. So this is what our x is going to look like. It's going to look like this. And so how do we actually find the largest x possible? Well, the easiest way to do it would be just to loop through each of these prime factors, look at the powers for each of them. And then for each one, we're going to construct a new x following these conditions and assuming that this power is the one that we're going to set to bi minus 1. So for example, we'll start with this prime and we'll set this to bi minus 1, everything else to ai. We'll calculate an x value for that. And then we'll look at this prime and we'll set this one to bi minus 1 and everything else to ai. And then we'll set an x value get a new x value for that. And we're just going to keep going. And we're going to get k x values, right? One for every single prime. And so out of all those x values, we just need to find the one that is largest. So we'll just pick the maximum out of all of them. So in summary, I guess I'll write it up. If P is not divisible by Q, then F equals P. Otherwise, prime factorize P to get primes. P prime, work out its power in P. Work out the new x. Sorry, I'm skipping ahead in my notes here. That shouldn't be there yet. For each prime in P, work out the new x if we were to set this power to ci bi minus 1, everything else to ai. Finally, find the maximum x out of all of these. Okay, so hopefully that makes sense. Are there any questions so far? You're by this algorithm? Give you some time to type in chat if you have any questions. But hopefully this makes sense. Since we're trying to maximize x, we have to use these following conditions. Set exactly one of them to be less than bi, and then for the rest, we'll just set them to ai to make it the maximum possible. And so Felix has caught on to an actually very important point here. Won't prime factorization be too slow? And I'm very good on you for spotting that, actually. Afaf says, then we only need the smallest prime from Q. The smallest prime from Q. Well, it might not necessarily be the smallest prime, right? For example, maybe the smallest prime, so let's just assume that these primes are in sorted order. You might not always want to set this to be equal to bi minus 1. Why? Because the difference in power between A1 and B1 might be very, very large. So for example, let's assume that A1 is like 1,000, and then this one is only like 2, right? And then we set this to 1. That would mean that we would have to get x from P, we would have to divide by this small prime to the power of 999, right? That's going to be very large. Whereas maybe if we had a larger prime where the difference was a bit smaller, then then we wouldn't have to divide p by such a large amount to get to it. So we do actually have to consider all primes. The example input 12 and 6 shows this. Yes, so I guess we'll have a look at it. 12 equals 2 squared times 3. 6 equals 2 times 3. And the answer was 4. So in this particular case, we chose to lower 3 instead of lowering 2. Okay. So that's that derivation out of the way. And let's return to what Felix was saying earlier, which is, won't prime factorization be too slow? I'm very glad you picked up on that. I was hoping someone would. So yeah, right here in this step, I'm telling us to prime factorize p to get the primes. But there's one big problem though. The problem is that p is up to 10 to the 18, and prime factorization is square root n, right? Square root of the thing that you're prime factorizing. So this is going to be problematic. I think there does exist a way to do log n prime factorization. I can't quite remember, so my apologies on that. But there is actually a workaround for it. So, does anyone have an idea for how we might get the prime factors of p without actually prime factorizing p? So once again, is there a way to get the prime factors of p without prime factorizing p? And this might seem like an impossible task, but I urge you to remember this one assumption that we made at the beginning here, that p is divisible by q. No, you're absolutely right. So, or you're half right, I guess. But basically, what we can do is we can prime factorize q instead. And remember, from our assumptions above, we remember that q must have the exact same primes as p. Right? So if we prime factorize q, we're going to find all the exact same primes that p is going to have. The p on q part is a little bit unnecessary because just prime factorizing q is going to give us all the prime factors that we need. Okay, so we can actually just prime factorize q instead, and then for each prime in q, work out the new x if we were to set its power to bi minus 1 and everything else to ai. So the thing is that when we do the prime factorization of q, we might actually miss out a couple of the primes from p. So for example, maybe some of these bi's are equal to 0, which would mean that this prime doesn't exist. So in reality, I guess maybe what it might look like is like pk minus 1. We might be missing a couple of primes, right? Maybe k minus 1 or k minus 2 or something like that. But that's kind of okay because it doesn't actually affect our next step here, which is since we want to, for every prime in q, we want to make the prime in x 1 less than that, right? So we do that for every single prime in q. And then the way we calculate the x is we just calculate how much we would need to divide p by to get the new answer. We calculate x by dividing p by the difference in the primes. I'll put difference in the primes in points. Basically, it's the difference between the original AI and this BI. That's right at the beginning. Each prime Q out the corresponding power in P. Just to go over it again, for every prime in Q, we're going to get this prime, and we're just going to work out the value of AI. And you can do that very easily just by dividing P a bunch of times until you get that value. And then after you get AI and you also know BI, then you can calculate the new x if you were to set the power to bi minus 1 and everything else to ai. And the way we do that is x equals just equals to p divided by exponential, and then what would the difference be? The difference would be the current prime to the power of ai minus bi minus 1. That would be the formula you would use. Where does this come from? Well, ai is the original. bi minus 1 is where we want to send the new power to in x. And so we just measure the distance between the two, and then we get the prime, that particular prime, to the power of that distance. And we just need to divide p by this power. Exponential is basically the same as power, and we will get the new value of x. And then out of all of these, we'll just find the maximum value of x. And so this will run in time. Hopefully that makes sense. And I think that that's the final sort of quote unquote mistake that we've sort of fixed in this problem now. So it should be all working. If there are any questions, I guess you could ask them now while I sort of start setting up for the coding section. Okay. So no questions? That is very nice to see. All right. Let's start by including our headers here. And so in this particular problem, it was you scan in integer t followed by t pairs. So what we do, so scan in t, and then t times it is going to call the function solve. And in solve, we're going to scan in p and q. Remember, p is up to 10 to the 18, so we have to use long ones here. And then now, right at the beginning, we can deal with this very easy case right off the bat. So if p is not divisible by q, then x equals to p. We can check non-divisibility just by checking that the modulo doesn't equal to 0. And if it doesn't, then we can just print out p and then return from this function. We're done. Now, if we ever reach this line of code, then we know that p is divisible by q. And so just get the prime factorization of q. We need to get a vector of pairs, and I need to declare pair in n equals pii. That's so my shorthand works. So basically, we're going to write this function now, and in this function, it's going to return a vector, and this vector is going to be a vector of pairs. And so each pair will be a prime and its power. So the first element of the pair will be pi, and the second element of the pair will be its power, so AI. So this is going to return this pair here. So let's code up this prime factorization. This is going to be exactly the same as the prime factorization you see in the tutorials. Won't be any, in the lectures. So it won't be anything too special. If you want sort of specific proofs as to why in particular, this algorithm works and it gives the exact prime factorization, I welcome you to look at the lectures. So in most cases, I think it's just enough to memorize this formula. I'll tell you a little bit about what's going on. I'll leave you completely clueless. So I here is going to loop from I to square root of n. That's what this thing is. And as it loops through, what it's going to do is it's going to pretend that I is the prime. And I'm going to check if n is divisible by I or not. So I'm going to start off with a power equals 0. And if n is divisible by I, then we're going to keep dividing n by I. So we're going to remove one factor for I at a time. And we're going to increase the power by 1 every single time as well. So if after this while loop, if power is larger than 0, then we found some sort of prime here. So we should push it back onto our vector here. So like that. I is the prime and power is the power. At the very end, if n is still larger than 1, then we can just push back on n. Why is that the case? Well, it's all based around the observation that if you do a prime factorization of n, there can be at most one prime that is going to be larger than square root of n, right? At most one prime that's going to be like that, and power is going to be 1. So if we go through n, if we go test all the primes up until the square root of n, right, and we find all of them, and then there's still one of the primes left, then that must be the prime that's larger than square root of n. And so we can just push that on directly with power 1. And then we can just return prime factors at the end of it. That's prime factorization there. This is order square root of n. Yeah, I think there is a way to do it in log n log n. I believe the idea is you just calculate all the primes using Aristotle's sieve, what's the name of it? Using the sieve, the prime sieve. And then once you have a list of primes, then you can just loop through them and test every single one. And so that will be just log n log n. So there do exist faster ways of doing it. I'm going to use the slow method, square root of n. Okay. So now that we've done that, we need to find, we have this list of primes now. We need to find the one that is going to be, we're going to set ci to equal to bi minus 1. So let's do the best equals 1. This is going to be the sort of best value of x that we've seen so far. Then I'm going to loop through primes of x. So I'm going to start set a equals 0. A is going to be the power of p. I'm going to do a very similar algorithm to what we did before. So n is going to become a copy of p. So we're going to set that. And then while n mod p, and I should probably define p as equal to pf. Well, actually, no, let's not do that. I'll do p. Instead, we'll use pfi.x, which remember, well, I need to define what x means. X will mean the first element in the array, and y will mean the second element. Sorry, first element in the pair, and y will mean the second element in the pair. So of course, remember the first element in the pair in this vector is the prime itself. So while n mod the prime is equal to 0, then n divided equals to pf I dot x, and then we'll increase a by 1. So after this, a will be the power of this prime within p. Let's also set p equals pfi dot y. Just for clarity, I remember dot y, the second element, is just the power of this prime. So it corresponds to this. And so let's calculate what we need to divide p by to get x. So we'll call it factor, and we'll make it exponential. Exponential, we'll get the current prime to the power of a minus e minus 1. Right, the distance between the original power and the power that we're going to set it to, bi minus 1. So this is going to be the factor, and of course, best just equals to the maximum of best, and p divided by factor. So p divided by factor is going to be the value of x that we calculate. We calculate the difference between p and this, and then so we just need to divide p by this factor to get the value of x. Then we can print out the best. Now all that remains is we need to calculate this exponential function as well, or we need to cook out this exponential function. So there are sort of two ways we can do this. There's a slow way and a fast way. I guess we'll start with the slow way, and, which is going to be sufficient to solve this problem, but I'll show you the fast way as well. So here we're going to calculate b to the e. We know that this is going to be able to be stored in a long. There's not going to be any overflow here, because b to the e is really, this thing here has to be smaller than or equal to a, and this thing here is one of the prime factors of p. So p to the a is clearly going to be less than or equal to p, which can be stored in a long run. So in other words, our exponential function is not going to overflow if we use long ones here. So I guess I'll show you the very standard way of coding it. This is probably what you've done in like Comp 511 when you're first learning about for loops, and like how to code them and stuff like that. You'll end up with something like this, right? You start off with answer, and then e times we're going to multiply our answer by b, and then we'll just return the answer. And this will be order b time. So this is actually going to be more than enough to solve this problem, mainly because, you know, this is going to be at most a, and the power of any prime is going to be at most log n of the of p, right? Log n of p. And so if we look at log n of p, which can be up to 10 to the 18, you see that this is at most 60. So this exponential function takes at most 60 steps, and that's relatively short run time. We'll actually confirm this properly later, but I think we can all see that with a complexity of 60, it's not going to be too big of a deal. But I just want to show you how to do fast exponentiation. So there are times in maths and number theory where you'll need to actually calculate the exponential, but much faster than order e time. And so this is where the fast exponentiation comes in. We can do it in log of e time. And this is overkill for this question. We don't actually need it, but I just wanted to show you. Okay, and the way this works is we'll start an answer with 0, and then while e, which means while e is larger than 0, what we're going to do is if e and 1, so if the first bit of e is set, then we're going to multiply answer by b. Then we're going to set b equals b times b, and we're going to bit shift b down by 1. Then we'll return answer. This might look very confusing at first, but it actually has a sort of relatively simple explanation. So what this is doing is it's basically doing bit operations on the value of e. Let's say e is equal to 1, 0, 0, 1, 1, 0, 1, right? And so this is the bit that represents 1, and then 2, and then 4, and then 8, and so on. So this is the least significant bit over on the right side here. And we have some sort of b. So the observation is that b to the e is just equal to, well, for every single bit that is set, we multiply it by b to the power of this thing up here. So if the first bit is set, then we multiply by b. This is not set. And then if this one is set, we multiply it by b to the 4, and then b to the 8, and then 32, 64, b to the 64. And so the idea is that b to the e is just going to be equal to this product of b's for these powers of 2 here. And so the idea is by looking at the actual binary representation of e and only multiplying b every single time that the bit is set, then we're going to get our power. So what does this actually mean? So basically what's going to happen is that each time we run the while loop, we're going to bit shift e down by 1. So in other words, what this means is that it's basically just going to delete the final bit in e. Right? So eventually, when we delete these bits, eventually e will become 0, in which case we stop. Otherwise, if e is not 0, so for example, we've reached up to here, then we look at the last bit of e, that's the and 1 bit over here. And if e and 1, which means that the last bit is set, then we change our answer, we multiply our answer by b. And each time we square our b as well. That's what's giving us this b4, b8, and then b64 here. So that's a sort of intuition behind fast exponentiation. And obviously, since we're actually looping over the bits of e this time, this is going to be log of e. It's going to take log e time to calculate the exponential. So this is a very, very nice solution. And I think that just wraps it up. So I guess the last thing that we need to do is we need to check the complexity. Prime factorize of q. This is square root n. So this is square root 10 to the 9, which is approximately equal to 30,000, I think. That's 30,000. Over here, we're going to loop through all the primes. Well, there's going to be log 10 to the 9 primes of q. So this is going to be just log 10 to the 9, which is equal to 30. Yeah, which is about equal to 30. That's equal to 30 here. Here we have to calculate the power, so we keep dividing it. But as we know, the power of a prime in P is also equal to log. So this is log 18, and they're doing it in P, not Q. So this is actually approximately just equal to 60. Then over here, our exponential, if we did it slowly, then this would just be the log of A, which once again is 60. But since we're doing it fast, we're doing a log of this. So this is just going to be equal to something very small, at 6. And so I guess multiplying these all together, we have this 30,000 times 30 times 60. And what we'll get is I suppose we'll multiply by the test cases as well. I think it's like 50 test cases. And then this will get us, 2 billion. That's a little bit larger than I expected. I think some of these are a little bit bigger than they should be. So I think the log here is going to be smaller. And I also think this log is going to be much smaller as well. These are sort of upper bounds. But I think in reality, they're going to be much, much smaller. So at the end of the day, this program does actually run in time. Okay, so I guess what we should do now is we should actually check that it does. It's not just me saying it, but we have to actually run against some inputs and see if it works. Okay, bunch of errors. So if I spelled prime factorized wrong somewhere. And I didn't print that properly. Okay, we got 10.4 and 179, which looks correct. I think it's time that we can submit this. And I guess while we wait for it to submit, I'll ask, are there any final questions about this code or anything that came up during the solution? We got accepted, very nice. So yeah, any questions, type them up, feel free to type them up. Otherwise, as a sort of conclusion, basically for problems that involve, I guess the key takeaway for this problem is that if it involves divisibility or division, multiplication, square root, or powers, it's often useful to think of these numbers in terms of their prime factorization. You'll probably get some sort of insight from doing that. Okay, if there's no issues there, I guess we'll move on to our next question, which is called the race. So for once, we're not actually going to use code forces. We're going to use a site called Project Euler. I was corrected this morning. I was saying Euler the whole time until someone told me that it's actually pronounced Euler. I've been saying it wrong my whole life. So Project Euler. If I make a mistake again, my apologies. Anyway, in Project Euler, and this problem is going to be about game theory and probability. So for this one, before we actually dive into the problem, I thought I'd explain what Project Euler is. Project Euler is a site that deals primarily with the sort of intersection between mathematics and programming problems. So there's a big archive of over like 700 problems, right? And each of them require you to solve some sort of mathematical challenge that normally you can't do by hand, so you will have to write some sort of program to do it for you. Project Euler questions actually work a little bit differently from the questions that we've seen so far. So far in competitive programming, what we've done is we've coded up a solution and then we've submitted that code and then tested your code against a bunch of test cases. However, for Project Euler, it's a little bit different. Instead of submitting your code, what it's going to do, it's going to make you write up a piece of code and it will run your code against some specific test case, and it's going to make you submit the answer to it. For example, we can look at this problem here. This isn't the problem for today. I just wanted to show you off like an example problem. We have the sequence of triangular numbers that look like this. And for each triangular number, you can write them as, in terms of their factors. So, 10 has the factors 1, 2, 5, and 10. 21 has the factors 1, 3, 7, 21, and so on. Now we can see that 28 is the first triangular number to have over 5 divisors or 5 factors, right? So the problem here is, what's the value of the first triangular number to have over 500 divisors? And the goal for you is to write a program to calculate for you. And then when you think you have an answer, so let's make a guess, you can try to submit it here, and I'll tell you if you're right or wrong. In this case, it looks like I'm wrong. Unfortunately, I was hoping I'd get lucky for this one. But yeah. So I kind of like these sort of problems. It kind of feels like, I'm cracking a puzzle every time I submit to it. They're a lot of fun. So the problem that we're going to be doing today is going to be called the race. And as you can see, I've actually already submitted to this one. So it just tells you the answer straight up. 0.836485556 is the answer to this one. But today we're going to be writing a program to confirm that this is actually the correct answer. Okay, so the problem actually looks like this. 2 players share an unbiased coin and take it in turns to play the race. On player 1's turn, the coin is tossed once. If it comes up heads, then player 1 scores 1 point. If it comes up tails, then no points are scored. On player 2's turn, a positive integer t is chosen by player 2, and the coin is tossed t times. If it comes up all heads, then player 2 scores 2 to the t minus 1 points. Otherwise, no points are scored. So in other words, the more player 2 chooses a larger t, then the less chance he's going to actually win, because he needs to he's going to need to get heads for every single t times in a row after t coin flips, right? So the more t that player 2 chooses, the harder it is for him to win, but also the more points it's going to gain. For every single increase in t, it's going to double the points he gets, but at the same time, it's going to halve the chance he gets it. Otherwise, no points are scored. So if he gets a single tails within these t coin flips, then he's going to get no points for that turn. Player 1 goes first, and the winner is the first to 100 or more points. Player 2 will always select number t of coin tosses that maximize the probability of winning. And so t can actually change every single turn, by the way, just to clarify. So for every single turn, player 2 can choose a different t, and he can flip that amount and then try to win like that. And the question is, what is the probability that player 2 wins? Give your answer rounded to 8 decimal places in the form 0. And then 8 numbers. So hopefully that makes sense. I'll give you 5 minutes to think about this problem before we come back with an explanation. And of course, during this time, feel free to ask questions. Yeah, it's actually surprisingly high. Right? Yeah, I'm actually very surprised that it's 0.8. That's like an 80% chance just by choosing t correctly. Hopefully by the time we write the program, we kind of sort of confirm that for ourselves that's true. It's kind of wild to think about, to be honest. Honestly, I don't have a good explanation for why it's so high. Okay, so hopefully that's enough time for you guys to think about it. Did anyone have any thoughts they'd like to share with everyone else? Have some time to type it out. If not, then I guess we can just dive into it. So I guess the first place to start for this sort of problem is knowing that this is a game theory problem. So what's a game theory problem? Well, game theory problems are generally problems where two players are playing a game, and the rules of this game are very well defined, and each player takes turns doing some sort of action. For example, player one takes a turn and does something, then player two takes a turn and does something, and so on. And for game theory, you can either have some sort of probability of winning, or it could be sort of predetermined. So if both players play optimally, then you kind of know already the outcome of the game before the game even starts. Depending on the game, it is. That's what a sort of game theory problem looks like. And it's worth knowing that most game theory problems are either going to devolve into greedy or DP solutions. So what does this mean? Well, a greedy solution for a game theory problem would be something like for every single turn, at every single state that you're at, there is always going to be one move that's obviously better than everything else, and that move is going to be very easy to calculate. So I remember from a couple, from the first week or the second week or something like that, we had a problem that was also game theory, and for every single turn, we worked out that it was always optimal to delete the longest sequence of ones. Right? That would be an example of a greedy solution. Every turn, there's some obvious move that you should do. For example, in this one, maybe a greedy solution might look like always choose t equals 1 for every single turn. Right? That would be a greedy solution. Otherwise, if a greedy solution doesn't work, then you might want to consider a DP solution. So DP, dynamic programming, what that would look like is that at every single state, so in other words, if player 1 is at A points and player 2 is at B points, that's considered a state of the game. At any state, what should your best move be? And the way you calculate that is by literally considering every single possible move that you could make and every single possible move that the opposite player could make in response, and then calculating the best possible result out of all of them. And then whichever move has the highest probability of winning at the end, you will make that move. And so this is how the DP is made. The recurrence is basically at every single point, you're going to make a certain move and let the opponent make another move, and then you'll arrive at a new state of the game. And so you can kind of see how this is quite equivalent to DP states, right? And you can calculate the probability of winning at a current state based on the probability of winning from other states. So that's where the DP comes in. So hopefully that makes sense. I guess the first thing we should start off with this question is to check whether there is a greedy solution or not. So one way that we could intuitively think about solving this question is always just choosing t equals 1. And there's kind of a reasoning behind this. So first off, let's actually calculate some values of t here. So for t, we'll go 1, 2, 3, 4, 5. And then for each of these, we'll calculate the probability of all heads. So basically the probability that you actually win that coin flip. And then we'll also calculate the score you'll get. So if you actually do get all those t heads, then calculate the score you would get if you won them. So I guess we'll start with t equals 1 here. The probability of getting 1 head in a row is what? I guess I'll just ask you guys, let's make sure that we're still awake and paying attention. What's the probability of getting 1 head? 0.5, very nice. And what's the probability of getting 2 heads? 0.25, very nice. and so on and so forth. The probability will halve every single time because we'll need one more additional head to get it. These are the probabilities for increasing t. And now we also calculate the score if we want. And so it gives us a very nice formula here. It's just 2 to the t minus 1. So here, 2 to the t minus 1 is 0. So 2 to the 0 is just 1. 2 to the t minus 1 here should be 2, and then 4, and then 8, and so on. So it should just double every single time. And so let's look at the expected value. Of, I guess, score for each of these is, well, to get the expected value, we always multiply the chance that something occurs with the number associated with the result. For example, half times 1, that will give us half. A quarter times 2, that will give us a half, and so on. And you can kind of see that all of these are actually the exact same number, which is half. In other words, no matter what t you pick, you can kind of expect that you'll get a score, an expected score of half if you sort of like average it out. And it kind of makes sense because as t increases, the probability that you win halves every single time, but the number of points that you'll get doubles every single time. So they sort of cancel each other out. And so you get potentially the same score every single time. Obviously, that's all sort of theoretical. What I should say is that the expected value is half, no matter what t you pick. And so it kind of makes sense that you would always want to pick t equals 1, because that has the least risk associated with it, right? This is like a general life lesson, but making small incremental gains is always better than like banking on one huge gain, right? So making like always choosing t equals 1, getting either 1 or 0 points, and then like over and over again is a lot safer than going for like 1 on 32, right? And then for a chance at 16 points, but you only have a 1 in 32 chance of getting 16 points. So that's the intuition behind it, and that's why you could kind of justify that maybe choosing t equals 1 at every single turn is the best possible option. So now that we have this greedy solution, it's my turn to sort of explain why this might not necessarily be the optimal play. So consider the following example here. Player 1 has 90 points, and player 2 has 0 points. Okay. So clearly, player 2 has a very small chance of winning, but we want to calculate exactly how small. Now, what I'm about to do here is basically going to be pseudo maths. It's not going to be real maths. We're not going to find exact values. But what I'm going to do is I'm going to use a lot of approximations, and I'm going to do a lot of hand waving. And I'm going to show you that the probabilities are nowhere close to each other. So let's first consider the example where we choose t equals 1. Right, so we just constantly choose t equals 1 every single turn, and we get a 50% chance of winning 1 point every single turn, right? Well, to win 100 games in a row, right, the probability of that, so if you were to win 100 points in a row, right, the probability of that is 2 to 100. And 2 to the 100 is equal to around 1 times 10 to the 30. So this is 100 games in a row. Right. So clearly this isn't actually the exact number that we're looking for. Obviously, player 2 doesn't actually need to win 100 games in a row. He can lose some games in the middle. So the real number will be a bit larger than this. Also, player 1, we haven't factored in the fact that player 1 needs to lose like 90 of his games, or 90 of his turns, in order to give the time for player 2 to catch up. So I'm actually missing a couple of details in this calculation, but hopefully we can see that just by looking at this raw number here, this chance is actually very, very, very small, right? We're talking 1 to the 10 to the 30. Even if I knock off a bunch of zeros off the end here, we're still looking at a very, very small number. So compare this to something like choosing t equals 8. So if we choose t equals 8, let's go back to our table here and sort of fill this in. If we choose t equals 8, then the probability of winning is 1 on, this is 2 to the 5, so 2 to the 8 here, which should be equal to 256. We have 1 in 256 chance of winning, and our score is 128. What this means that we have a 1 in 256 chance of winning, but if we do, then we instantly win the game, right? We instantly become over 100 points, so we just instantly win. We have a 1 in 256 chance of winning. Right, so this is a 1 in 256 chance. And so hopefully we can see, and once again, this isn't quite exact. Obviously, in the actual game, player 1 is, player 1 is going to take some time to actually reach 100 points, like maybe like around 20 turns or so. So in fact, we're actually going to have like 20 or so turns of this 1 in 256 chance to get to win the game, right? So obviously this also isn't the exact number that we're looking for, but hopefully by my sort of pseudo maths and a bit of hand waving, you can kind of see that these two numbers are wildly different. One of these numbers is much, much, much smaller than the other one. And so hopefully I can sort of use this as a sort of, at least to give you the intuition that perhaps it might not always be the case that you want to pick t equals 1 and make small incremental gains every single time, right? Sometimes you do want to pick a large t and bank it all on like a very small chance to win a huge ton of points. And this is especially the case when you're extremely behind. So when you're extremely behind, you tend to want to use large values of t. When you're ahead, you tend to want to use smaller values of t, right? To sort of guarantee that you stay ahead. That's sort of the intuition behind it. And what this sort of means, why we sort of did this, if you remember, we were trying to show that this greedy solution doesn't quite work. And if the greedy solution doesn't quite work, then perhaps we will need to consider a DP solution. So let's dive into this DP solution now. So this DP solution is going to take quite long. I think we're going to be going all the way up until 5 o'clock, if that's okay with everyone. So I guess we'll start off with the state. Luckily, the thing about doing DP in game theory is that it's much easier than doing DP for any random DP problem. And the reason why that is because all game theory problems have the same structure for a DP. The state is always going to be the state of the game. So we define DPAB equals the probability player 2 will win. If player 1 has A points, player 2 has B points, and it is player 2's turn. Right, so this is the state here. I will note that for most game theory problems, sometimes we'll have an extra variable here called t, which will represent the turn that it's on. So in a lot of game theory problems, it might look something like this. This t will represent which turn you're on as well. And that's prevalent when both players have some sort of agency in their turn. So if both players can make decisions, then you might want to choose t here because player 2 is going to maximize player 2's chance of winning, but player 1 is going to maximize or minimize player 2's chance of winning. So in that case, we'll need an extra variable here. But in this particular problem, player 1 actually has no agency at all, right? All player 1 does is he tosses the coin once. If he gets the head, then yippee, he gets 1 point. If he doesn't, then he gets no points. But he doesn't get any choice at all about how to play his turn. Whereas player 2 gets to actually choose the t times that he flips the coin. So in this particular case, we don't actually need to put the turn into our state. we can just be satisfied with saying dpab is the probability that player 2 will win, given the state A and B, and given that it's player 2's turn. That's going to be our state. Next, we need to work on our base case. So I'll ask you guys, what do you think the base case would look like for this particular DP? There's going to be two base cases here, two main ones that we need to think about. No ideas? Well, the base case for game theory problems is always going to be the end state. So it's going to be the state when the game ends. So in other words, either player 1 wins or player 2 wins. So we should calculate this. So B is larger than or equal to. Remember, B is player 2's score. Larger than 100, then the probability is 1. If A is larger than 100, then the probability is 0. Hopefully that makes sense. If we reach 100, then we get a probability of 1. We're definitely winning. If we're at a state where A is over 100, then the probability is 0. Now that this order is actually very important as well. We always want to check the probability of B first and then A. Why is that? Well, when we're at a certain state, it's totally possible that so like this state, the state describes the probability of winning at player 2's turn. So to transition from one state to another, first player 2 needs to make their turn, and then player 1 also needs to make their turn as well. So it's sort of like 2 turns in order to get to the next state. And so it's totally possible that from one state to another, both players actually end up winning, right? If we calculate both of their turns, both of them end up above 100. And so that's why it's important that we check player 2 first, because if player 2 gets to 100 first, well then he wins first, not A, right? Even if they both get to 100, since player 2 goes first, then player 2 is the one that actually wins. So it's very important that we check B is larger than or equal to 100 first, and then we check A is larger than or equal to 100 second. So hopefully that makes sense to you guys. And next we need to do is how to actually get the answer. So by answer, what I mean is this final answer here. I want to calculate the answer, so I want to put it into this variable, and I want to use some values of dp that we've calculated before. So let's assume that we've already calculated all the values of dp. How can I use them to work out what my answer should be? Ideas? Okay, well, as a hint, maybe you should consider sort of what player 1 can do here. So to start off with, this is the probability that player 2 will win given this particular state, and it's player 2's turn. But as we know, this game starts off with player 1's turn as well. So you need to consider what player 1 does on his first turn. And so what player 1 does is, well, there's actually sort of two options that player 1 can do. Either he wins his first coin toss or he loses his first coin toss. And each of these has a probability of half. Okay, so let me ask you this. If player 1 loses his first coin toss, what is the probability of us winning in terms of the DP state? So I'll say that again. If player 1 loses his first coin toss, if player 1 loses his first coin toss, then what is the probability that player 2 will win using these using the calculated values of DP? Exactly right, Bowen. The answer is DP 0, 0. Like that, well, if player 1 loses, then the points will be 0 points each, right? All of them will start with 0 points, and it'll be player 2's turn. So just by the definition of our DP here, DP 0, 0 would be the probability that player 2 wins if both of them start at 0 and it's player 2's turn. Of course, this probability happens with a half because player 1 only has half 0.5 chance of losing the first turn. And now we also have to consider what happens if player 1 wins the first turn. So what's the probability of player 2 winning if player 1 wins his first turn? Hopefully this shouldn't be too much more difficult once we know the first solution. I'll repeat the question again. What's the probability of player 2 winning if player 1 wins his first turn? Yeah, exactly right. DP 1, 0, right? So I think he won his first turn, it's going to end up on 1 point. And again, we divide by 2 because this has a half chance of happening. And this is our answer. We consider the two cases for player 1, multiply them by half, and we look at the probabilities of winning. And that's how we get our answer. Okay, excellent stuff. Now I just have to work on our recurrence, and this is going to be the hardest part. This is going to be quite a lengthy part, so strap in. Okay, so for each state A and B, we need to find the best value of t to use. For each t, what we're going to do is we're going to calculate the probability of winning if we use that particular t. First off though, I need to ask a question. What's the maximum t that we would ever go for? That player 2 would ever use? What's the maximum? 8. And why do you say 8? Right, he gets 128 points if he wins, which is over 100. In other words, he wins instantly if he wins the 8, like the 8 coin tosses. There's no point in going any higher than 8 because the result would still be the same. He would still win instantly, but his chances just get lower and lower and lower, right? So in other words, we only need to test for t is between 1 and 8 for every single state to see which one is the best. So that's very, very useful for us. Let's define a bunch of variables now. So let's fix t. We're going to fix the t to a certain value. I'm going to define win1 equals a chance that player 1 wins, gets ahead, right? Or I'll say it wins this turn. Player 1 will win this turn. This is just equal to 0.5. I'll define win2 equals a chance that player 2 wins this turn. This chance is 1 on 2 to the power of t. Right? That's just going to be this value over here, the chance that he gets t heads in a row. Then we'll define lose1 equals 1 minus win1, lose2 equals 1 minus win2. This is pretty straightforward. It's basically the chance that player 1 loses and the chance that player 2 loses for that particular t. Okay, that's pretty straightforward. And now to move from one state to another, we need to consider 4 different cases. And I'm not going to type it all out, so I'll just copy paste it from my notes. Here are the 4 different cases. So case 1, player 2 wins, and then player 1 wins. Case 2, player 2 wins, player 1 loses, and then so on. So all the combinations of losses and wins for player 2 and then player 1. So for each of these cases, we're going to see how this sort of transitions us into our next state. Okay, let prob of I be the probability that case I occurs. And you can calculate this just by using win 1, win 2, lose 1, and lose 2. So for example, the chance that player 2 wins and player 1 wins is just win 2 times win 1. For case 2, the chance that this occurs is just win 2 times lose 1. So prob of I is also very easy to calculate just based on win and lose. Let prob t be the probability that 2 will win over all after choosing t at this state. Right. And so we'll get the formula that prob t just equals to the sum of prob I times prob of winning after case I occurs. So for each of these cases, we multiply the probability that the case occurs with the probability of winning after that case occurs. This should be I. If we sum them all up, we'll get the probability of winning by choosing this t. So since we consider all possible cases, then prob t is just the sum of these cases. Hopefully we're making sense so far. And next, what we need to do is we need to find what these cases should be. And luckily, once again, this isn't too difficult. So we define the following: that case I be the probability of winning after case I occurs multiplied by the probability of case I occurring. In other words, what case I is really just equal to this thing inside the bracket here. The probability of winning after case I occurs multiplied by the probability of case I occurring. So in fact, you could just replace this with case I, and that would be equivalent. Okay. How do we actually calculate these case I's though? Well, this actually isn't actually too hard. So case 1 should be equal to the prob of 1, right? We calculated that earlier, and then we multiply it by something. What do you think we should multiply this by? And we'll come back to our, remember this is a recurrence, so we're going to be probably using the value of dp again. What arguments should we pass into this dp to get the probability of winning after case I occurs? No ideas? Well, after case 1, player 2 and both player 1 wins, right? We can see that up here. So we should query what happens if player 1 gets 1 point and player 2 gets 1 to the 1 bit shifted t minus 1. And if you're not familiar with this notation, 1 bit shifted 2 minus 1 is just shorthand for 2 to the power of t minus 1. So basically what we're going to do, we're going to add on both the points onto the state, and then we're going to query dp at that new state, right? We're going to get the probability of there as well. And by the definition of our dp, this is going to work as exactly as we want it to. I guess up here, I should clarify that we are at state AB and the t is fixed. Okay, so this is case 1. And what I'm going to do is I'm just going to copy paste over all the other cases from my notes as well, because I can't be bothered to write them out. I believe case 2 and 3 need to be swapped. Okay, so we end up with this. And finally, prob t is equal to case 1 plus case 2 plus case 3 plus case 4. So for a given t, all of these values are calculatable, right? Prob 1, prob 2, prob 3, prob 4 are all calculatable. All these values are calculatable as well. They're just the recurrence of our dp. So we know what case 1, case 2, case 3, case 4 is, and hence we can construct a DP off of that, in theory, right? Before I move on into why this might not be, why there might be a problem with this sort of solution, is everyone following along with the definitions I've discussed so far? So all the 4 cases, what each of these variable means, prob 1, prob 4, prob t, all of these variables. Just want to check that if there are any questions about that, because we're going to be using them a lot in the upcoming section as well. No questions? Okay, very, very nice. Okay, so DPAB. So I guess as we just discussed, for some t, for some fixed t, we can calculate this prob t here. Then dp max AB will just be with the max prob t for t between 1 and 8. Right, we'll just test every single t between 1 and 8, and we'll get 8, and we'll get the maximum out of all of them. Did anyone spot something wrong with this though? Something wrong with this recurrence? There's one problem with this. As a hint, think about this particular term right here. Why is that term problematic for us? Not sure? The reason why this term is problematic is because we're relying on the value of dPAB to calculate dPAB, right? This is a problem. You can't have a dP that relies on its own state to calculate the state. So this we have some sort of error that we have to fix here. But luckily for us, this actually isn't too hard to fix. So let's fix t one more time. Let's say that t is the optimal solution, right? So if t is the optimal solution, in other words, this value of t is going to give us the best probability of winning at this state. If this is the optimal solution, then prob t is equal to dPAB. So since we have this thing here, well, case 4 is equal to prob 4 times dPAB, and prob t is just equal to dPAB as well. So rearranging this, what we'll get is dPAB equals the sum of all of this divided by 1 minus prob 4. In other words, if t is the optimal solution, then dPAB is equal to this formula here. Remember that case 1, case 2, case 3, and prob 4 are all dependent on t, because all the probabilities are based on win 1 and lose 1 and so on, and win 2 and lose 2 are all based on t. So for a fixed t, this is all actually dependent on t, and if t is the optimal solution, then dPAB is actually equal to this result. If t is not the optimal solution, then the following happens. So prob t would be less than dPAB, right? dPAB stores the optimal solution, so prob t would be less than that if t is not the optimal. So we will get, since prob t is equal to this thing must be smaller than dPAB, right? On this line over here. Once again, we can expand case 4 to become prob 4 times dPAB. So once again, rearranging, what we'll end up with is the exact same formula as before, but dPAB is going to be larger than this amount. Right? dpab is going to be larger than this, this same equation for t. So what does this tell us? Well, what it means is that if t is the optimal solution, then dpab is going to be equal to this calculation. If t is not the optimal solution, then dpab is going to be larger than this thing that we calculate. Okay, well then, if we were to just, for every single t, we calculate this particular formula here, right? And then we take the maximum out of all of them, then that must mean that it is equal to dpab, right? If we take the maximum out of all of these formulas for every single t, then the maximum of them must be equal to dpab, just because since dpab is equal only when it's the optimal solution, dpab is larger than whenever it's not the optimal solution. So our conclusion is that hence it suffices to find property such that the equation, this thing, is maximized. Or we'll call that t. Find t such that the equation of t equals that is maximized. Okay. So in summary, I guess we'll do one last summary here. We tried the greedy solution and it didn't work, so we moved on to the dp, and our dp was this particular state here. For each t, calculate thing like this, take the best, or property equals that, take the best probability to be dpab, and that's going to be how we handle our occurrences. So that's pretty much it. Are there any questions about this at all? I guess while we get set up, if there are any questions, feel free to ask them while I get set up for the tutorial. Any questions? Okay, very nice. I'm going to copy paste the majority of this code of this stuff into here as well. I'm not going to bother with correcting the lines. That's going to be way too much effort. Okay. Let's get coding here. Need that. Need algorithm. I think that's all we need. Okay, so the way we're going to do this is we're going to do a top-down DP. So we'll grab our state from the very top here. And we'll sort of define LD, DP A into B. What is LD? Well, I haven't defined it yet, but I'll tell you. LD stands for long double. So long double is the sort of highest precision that you can get in C++ with floating points. So we like to use LDs here to get the most possible precision. To be honest, you could probably get away with using floats or doubles. They're probably going to be fine, but we just want more efficiency because why not? Okay, start off with our DP. Well, I guess what we want to do is we want to memorize stuff. So add these two variables here. So the done array just tells us if we've calculated this DP value before, and the memo just stores the previous value that we've calculated before. So initially done is all zeros, and we're going to, as we calculate DP values, we're going to fill it in. So if B is larger than or equal to 100, return 1.0. If B is smaller than, if A is larger than or equal to 100, return 0.0. Right? This is the base case that we talked about earlier. Then if we've actually done this before, then we can just return memo AB. Cool. Otherwise, we'll set done equals true, and then we'll make sure that after we calculate our answer, we also store it in our memo as well. Okay, so let LD best equals 0.0. This is going to be the best prob T that we see. I'm going to loop through all the values of T, and I'm going to calculate that formula. So let's first calculate the probabilities they are winning this term. Win 1 equals 0.5. Only win 2 equals 1.0 divided by 1 bit shifted T, or 2 to the power of T. Lose 1 just equals to 1.0 minus win 1. Lose 2 just equals to 1.0 minus win 2. Okay. Calculate the probabilities of each case occurring. And we have 4 cases. So early prob 1 equals to, well, let's actually look at our cases. Where was it? Player 2 wins, then player 1 wins. And then case 2 is player 2 wins, and then player 1 loses. Okay, so the first one is both of them win. The second one is player 2 wins, and then player 1 loses. The third one is player 2 loses, and then player 1 wins. And the final one is both of them lose. The probabilities, we calculate case 1 to case 3. Probability of each case multiplied by probability of winning if it occurs. And I think we wrote it up here, so I'll just copy paste this. So we'll have each case. We have case 1 is probability of 1 times the recurrence of the DP. Case 2 is probability 2 times the recurrence of the DP, and so on. Right. I remember we can't actually use case 4 because it refers to itself for the answer. So we've got to make sure we don't actually include that. All we need is case 1 to case 3, and that's actually all we need for our formula. If you remember here, this formula just needs case 1 plus case 2 plus case 3 and prob 4. Finally, we calculate probability of winning if we choose this T. LD prob T is equal to case 1 plus case 2 plus case 3 on 1 on prob 4. This is the formula that we decided on earlier. And finally, best equals the max of best and prob T. Finally, at the end of this for loop, we'll have to calculate the best probability. So we'll make sure we update our memo. Memo of AB is equal to best, and then we'll return that best value as well. Finally, all we need to do is we need to make sure we print out the correct number. So what we'll do is call 0.0 2 plus DP 10 on 2, which is how we got the answer that we calculated earlier. To get 8 decimal places of precision in our printf statement, what we need is to do a 0.8 here. The 0.8 there, and that's just going to tell us, tell the compiler that we want to print out this long double up to 8 decimal places. So hopefully that works. Let's try to run our code and see if I've left any bugs in there. A lot of bugs, it seems. Right, so if we're going to define what max n should be. Okay, what I want to do is I want to define max n as, well, firstly it has to be at least 100, right? Because it's going to be from 0 to 100. But remember, when t equals 8, we could potentially win another 128 points on top of that, right? So you can imagine a scenario where player 2 is on 99 points, and he rolls for 128 points and gets it. So you have to make sure that there's enough room in the array for that to happen as well. So we'll do max n equals this thing here. All right, looks like we have one final error here. I accidentally used I instead of T, so let's make sure we correct that. And we'll get a number. With a percent at the end, that's because I forgot to put a /n at the end. But hopefully we can see it's very small, but hopefully we can see that that number says 0.8364, 8556, and this number here is 0.8364, 8556. This is the same number. We were able to calculate the same result using our DP. So are there any final questions about this code before I give my sort of concluding thoughts on this? No more questions? Okay. So I guess just to finish off on this this question, firstly, one of the key takeaways here is to use for game theory problems, like the solution is either going to be a greedy or a DP, right? If you try to find a greedy solution and it doesn't work, then you should consider trying to use a DP. And a DP solution is normally quite easy to set up. The state is always going to be the state of the game, potentially with the turn that the player is on. And the base case is always going to be the end state of the game. Also, something else I want to point out, for this topic in particular, which is maths, sometimes you might end up having to sort of translate equations into code. And so one thing I highly recommend you do is you use a lot of variable names, a lot of different variables. Like for example, here I've used like 12 different variables just to calculate this one equation here. I didn't actually need to do this, of course. For example, I didn't need to have a variable for lose one. I could have just replaced all lose one with, 1.0 minus win one, and it would have all been the exact same here. But the reason why I did do this is because it makes the equation much nicer to read. It splits it off into very nice readable chunks, and this will also help you with debugging. So if you ever come to a situation where you need to translate an equation, like a math equation, into code, make sure you like break it into a lot of different chunks for each of the terms, and then sort of put it together like that, so that it sort of becomes very nice and readable. Okay, so I guess that's it for this DP solution and this question in general. So hopefully you've learned a little bit about game theory and probability from this. For the last sort of 8 minutes before 5 o'clock, what I thought I'd do is I'd share some exam advice. So this would be just sort of 5 tips that I sort of learned over the years, and I've also seen students mess up the same things. So 5 pieces of advice that I give to you for your final exams. So I'm going to list them all out so that you can see them all. Okay. Number 1. Read all problems carefully. So what does this mean? Basically, when you're reading a problem for the first time, make sure that you read every single word. Purposely read every single word. Read it out slowly, and if it helps, read it out loud. So basically, what I want you all to do is I want you to do it exactly the way I do it in tutorials. How do I do it in tutorials? Well, let me grab a more conventional problem. So let's go back to code forces. So what I do when I'm reading out problems for you guys is I make sure I read every single word, right? I never skip anything, even if it looks like flavor text. So for example, all the favorite subjects are history and maths. This might seem useless. Make sure you read it anyway, because if you skip sections and then you end up skipping something useful, well, that's just bad on you. Read every single word. Take note of the bounds. Sometimes bounds can give you hints. So even as you're reading the input, read the bounds. Even if you think you know what the input should look like based on the problem description, read the input anyway, because there's always potentially some information. Maybe you misunderstood something in the problem, and it gets cleared up when you read the input. Same for the output. Make sure you read that, and make sure you do the sample cases as well. And by doing the sample cases, I mean actually do them out by hand. Make sure you can confirm for yourselves that, yes, these sample cases make sense to you, right? That way, you can sort of make sure before you start the question, you're guaranteed that you sort of fully understand the question. That's the first tip. Read all problems carefully. Also, as a sort of add-on to this as well, before you even start coding, read the problems for all problems, right? I think in the final exam, the course outline says that there's like potentially up to 8 questions. So make sure you read the problem statements for all 8 questions. Yep. Before you even start, they'll tell you, which questions are easier than others, which one you should probably start with, and stuff like that. Also, especially for these sort of contests, is they have subtasks, right? So we already saw in contest 3 how you had 6 problems, but it was really just 3 problems, and then each problem was split into 2 subtasks, right? Make sure you read both of the subtasks carefully as well, because sometimes there could be differences between the 2 subtask statements. In contest 3, they were the same for both of them, but that might not be the same for content in the final exam. So make sure you read all the subtask problem statements properly as well. Okay, next step, and this is probably my most important one, never spend too long solving a problem. I think this one, I've seen actually a lot of students fall into this trap, and I myself have actually fallen into this trap a ton of times. And it's sort of the temptation of the sunken cost fallacy. So in other words, I spent 30 minutes on this problem already. If I sort of give up now, then this 30 minutes is wasted, right? So I should stick to this problem. And then what ends up happening is that you end up sticking to this problem, and then 1.5 hours pass by, and you realize, I've just wasted 1.5 hours, I haven't made any progress, and I haven't given enough time to all the other problems. So it's very important in these contests to manage your time properly. The bottom line is, a good sort of guideline is, if you spent 10 minutes on a problem and you haven't made any progress or observations on the problem, perhaps you should consider switching problems, because there might be other problems that you haven't given as much attention to, and that might turn out to be much easier than the problem that you're currently working on. Also, as well, just taking a break from the current problem may give you some inspiration when you come back to it. So yeah, never spend too long solving a problem. Have a sort of 10-minute sort of limit. Like if you have 10 minutes and you haven't made progress, switch problems. Third piece of advice, test as you code. So what's testing? It's basically just unit testing. So in other words, you want to code your program, you want to divide your program into like sort of small chunks, small logical chunks, and you want to test them as you code them up. So for example, maybe you have a range tree question and maybe you're not quite confident in coding range trees. Then before you even scan in input, before you even like code the scanning in of the input, try to code a range tree, right? Code the query function, code the update function, and then check that it works with a few handmade cases, right? And only once it works, then you can start coding in like the scan in and scanning in the inputs and like how you're actually going to handle it. But basically what this means is that each time you move on to the next bit of code, you're sort of guaranteed that the previous bit of code is going to work nicely, right? So you have this confidence that the previous bit of code is working as intended. This is more useful the less confident you are in your coding skill as well. So for example, if you're just like, coding a for loop through an array, and it's like a prefix sum, you're calculating the prefix sum, and you've done prefix sum like tons of times before, you know exactly what it looks like, then fine, then test it, right? But if you're maybe coding prefix sum like the first or second time in your career, then maybe you might want to actually double check that your prefix sum is actually, giving you the prefix sum. So print out the stuff inside the prefix sum, make sure it's working before you move on to the next step. That's step 3, test your code. Next is step 4. If you get stuck, reread the problem. So this is something that often gets forgotten when bug fixing. So you always get to that situation where, okay, well, maybe you've been thinking about this problem for a long time and you haven't made any progress, or maybe you've been trying to debug your program for a long time,
but you can't figure out why it's wrong, right? You can't figure out why it's getting WA or wrong answer or time limit exceeded. If that's the case, one thing that you should try is to reread the problem. So it actually happens a lot of the time, even if you do step one, even if you read the problem carefully, sometimes there's still room for misinterpretation and there's still room for missing some important information. So if you get stuck, reread the problem. You'll sort of refamiliarize yourself with the problem and what it's asking, and you'll make sure that you're not missing everything or not missing anything. When you reread, you should do the exact same thing that we did before. Read it very slowly and read it out loud. I find reading it out loud sort of helps make sure that I generally do read every single word instead of skimming over it. So this is sort of last-ditch resort. If you can't figure out what's wrong, try rereading the problem. And finally, my final tip, take regular breaks. So this competition or this final exam is going to be 6 hours long, right? This is a very, very long exam. It's going to be longer than any exam that you've done so far, probably. And it can get tiring at times, right? You're sitting there in a chair for 6 hours straight trying to solve informatics problems, competitive programming problems. And so it's important to take breaks to restore your mental energy. So if this wasn't COVID, what this would mean is that you would put your hand up and you would say, I need to go to the toilet. And then they'd say, okay. And then while you're walking to the toilet, that's your break, right? You can sort of walk around inside the toilet. You can sort of like jump up and down if that's what you like to do. And you sort of have some time alone to sort of think about it. And it's actually surprisingly helpful. You won't believe the number of questions that you can solve while sitting on the toilet. But since this is COVID times, we're actually doing this contest in the comfort of our own homes. And so we should use that to the fullest advantage. So, you're in your own home doing a 6-hour contest. If you ever start to feel tired or maybe even panicked, right? If you're like feeling like, you're screwed or something like that, take advantage of the comfort of your home. Lie down on your sofa, watch YouTube, like pace your room, whatever you need to do, right? Just relax for a little bit. You can do this for like 10 minutes at a time. Ultimately, 10 minutes in a 6-hour contest, that's not going to affect your marks. Like, let's be real. And ultimately, it's just going to sort of rejuvenate you, restore your mental health a little bit, and make sure you're not as stressed. And by doing that, it sort of just helps you, put you into a better mental state to be able to solve problems. So that's tip number 5, take regular breaks. So those are my sort of 5 tips for sort of competitive programming. I guess now that that's out of the way, we can go on to our problem set. So the problem set for this week, week 8, problem set 8, I like to point out, has a time limit of 3 weeks this time. It's not 2 weeks, so you'll have an extra 1 week to actually solve this particular problem set. So hopefully that's useful for you if you're sort of feeling time pressure for the final exams. Once again, I'm always happy to answer questions about the problem set, whether it be this week's. Of course, this is going to be the final tutorial, so this is the final tutorial where I can help you with problem set 7 or problem set 8. And especially problem set 7 specifically because it's going to expire soon. So this is going to be the final tutorial that I can help you with that. Also, if you still have problems that you want to ask about, whether it be like problem set 8, problem set 7, well, I'll repeat that since I thought I might have reconnected there. If you do have any more problems that you want to ask me about, such as from problem set 8, problem set 7, or even just any informatics or competitive programming problem that you find that you're trying to do in training for finals, just email me, right? I'm always available to help. I'm always very, very happy to help. It's very fun to help you guys solve the problems. I love it. And yeah, even if it's finals, don't think something like, Kevin's like studying for finals. I'm not going to message him. Do it anyway. I love to help out. So yeah, even during finals, make sure you email me. And that's pretty much all I have to say about the problem sets. I guess since it's the final tutorial, I'd like to say thank you very much for coming to the tutorial for all this time. Even you, Bowen, for coming in the final week. I do very much appreciate it that people are still coming and still listening and still finding some sort of value in my talking. So yeah, thank you very much. You all have shown that you're very sort of determined in coding and you're willing to put in the effort to do well in this course. So I'm sure that in the finals, you'll all do excellently well. So thank you very, very much for coming to my tutorials. Okay, so thank you, thank you. All right, so what I'll do now is I'm going to set up the breakout groups. So answer with the problem that you're doing, whether it be from problem set 7 or problem set 8, and I'll put you into your groups. Gonna run? All right. Good luck with your finals, Felix. Goodbye. You too, Marilla. Good luck. Best of luck to you. Good luck, good luck. See you when I see you. All right, Bowen, what question are you up to? Could you please fill out the multiple choice form? Excellent stuff. Okay, I'll put you in group 1 with R5. All right, so I'm gonna open up the breakout groups in a second. It's gonna take me a little while to get to your groups since I need to make the paste bins for you guys for this problem set and upload the problems and stuff like that. So take the opportunity to get familiar with the problem once again before I come around. The final tutorial.